Hi everybody, welcome to this presentation by Laszlo and me on a correctness result for synthesizing plants with loops in stochastic domains. This is a journal paper and it's part of the journal track at ICAPS. So the key object of study here are finite state controllers. These are massively popular examples of plants with loop because they're powerful and compact for capturing a whole range of different kinds of plant structures. They're used in robotics, video games, and logistics. Just to give an example, for instance, you might have this kind of linear hall where the agent starts in state A and it has to progress to state B, and it might not be clear how many rooms are in between. So you could have 3 rooms, you could have 2 rooms, or you could have 100 rooms, and essentially the same plant structure would accomplish satisfying this goal because you could have a loop in the sense that as soon as there's a room, the agent progresses forward until it reaches the state B and then it stops. So this kind of plant structure is the one on the right. You can think of cleaning a table where you don't know the number of objects on the table. You could think of chopping a tree with an unknown thickness. And for all of these problems, having such a recursive plant structure basically can be used to solve all of these problem instances. There's a lot of work on algorithms for synthesizing these finite state controllers. Things like and or bounded search, abstraction, etc. We discussed this in the related work. The point of topic in this talk here is we are considering the situation where actions are noisy. So there's some non-determinism with the actions and potentially with the probability distribution on the outcomes of these actions. So for instance, we can imagine an agent that's standing at the handrail of a bridge. On one side is a sidewalk, on the other side is a river, and the agent is n steps away from the goal. So with every step taken on the handrail, the risk is that the agent has a 0.1 probability of falling into the river, which is an absorbing state because we're going to assume the agent cannot recover from that, or it has a 0.9 probability of moving forward by 1 step. There is this option, however, that the agent can get onto the sidewalk by jumping onto the sidewalk, and there the forward action is deterministic. So of course, if you think about this, if you move solely on the handrail, the probability of goal satisfaction is 0.9 raised to the power of n, because the agent is n steps away. But of course, the agent can also do better. Right? So for instance, if you want to accomplish this goal with a probability of 1, what you would do is this plant structure on the right hand side at the top, where you climb up on the sidewalk, okay, you move forward until you reach the goal, and then you get off the sidewalk to the goal, and then you're done. And of course, because this is completely deterministic, so we are assuming only the move on the handrail is noisy, everything else is deterministic. This accomplishes the goal with the probability of 1. On the other hand, if you wanted to accomplish this with a probability of 0.9, you could consider doing one move as long as it's not the goal forward on the handrail. So there's a 0.1 chance of falling off, but for the remaining moves you could climb up and move on the sidewalk and get to the goal. So there are all of these possibilities in terms of how you can satisfy the goal, and depending on the correctness likelihood that you're looking for, potentially different plant structures are interesting. So the reason we might prefer a plant structure with the lower probability is, of course, in some more complicated situations, it might be hard to achieve, or it might be costly to achieve a perfect run, and so you're looking for a slightly slightly riskier runs to save cost and other kinds of resources. So that's the kind of reason you might be prioritizing a lower likelihood than the full one. Now the question is, how do you handle this kind of noise? Although there are lots of approaches for synthesizing finite state controllers, as I mentioned, including some in the noisy setting, especially in the MDP and the POMDP literature, we note that many of them either approximate how they compute these policies, these plan structures, or they do not properly handle non-terminating traces. For instance, they might assume that failure cannot happen infinitely often. And indeed, you can kind of show that a very popular and/or bounded search algorithm fails if at least one history is there that cannot be extended to a goal history. And again, this algorithm fails if there's at least one looping history. So in some sense, just taking a deterministic algorithm and somehow determinizing the problem domain might be one way to solve it, but there is no way to exploit the probabilities. There is no way to exploit the trailing probabilities on looping, and this is why it kind of makes sense to think whether we want to have a slightly more robust algorithm in the presence of noise, and that's precisely what we're after. So the planning problem we're interested in can be specified as follows. Let's call the likelihood of goal termination as simply summing up the probabilities of the histories that lead to the goal, right? So you're looking at traces and you're collecting those traces that reach the goal, and you're looking at the sum of all of this. So let's call this a likelihood of goal termination. And the way we are specifying the planning problem is as follows. We are considering states, actions, observations as usual. We are considering a stochastic transition function, so that's this delta here. We are considering a deterministic observation function, so every state will tell you the observation. It could be that this observation is not very informative, but nonetheless the observation function itself is deterministic. There is an initial start state, that's S0, and a goal state, G. Okay, so this is a planning problem, fairly standard. What we have is an integer n and a desired likelihood of goal termination LGT star, which is between 0 and 1, and the task here is to find a finite state controller with at most n states, so you don't want it to be unbounded. You want a bounded finite state controller such that the LGT, the likelihood of goal termination from this controller, is at least or better than LGT star, right? So you're achieving for something better for this planning problem. Again, I reiterate that it's only this the transition function that is stochastic, okay? So this is the planning problem, and here's a theorem we have. We basically can prove that given a planning problem P, integer n, and LGT star, there is an algorithm we provide that is sound and complete, okay? So essentially, every finite state controller C returned is n-bounded. It has at most n size, and certainly its LGT is at least equal to or better than LGT star. And if at all, so this is a soundness part, and the completeness part says that if there exists an n-bounded controller such that LGT is greater than LGT star, then one such FSC will be found. Okay, so that's the theorem we can basically prove. So how do we do this? To do this, it's worth quickly recapping the nature of the standard deterministic and/or bounded search algorithm. And how the algorithm works is that it starts with an empty controller. It guesses a finite state controller with an initial state Q0 and the state space initial state S0. Okay, it starts with this, an empty controller, and it has two functions and or and that alternate with each other. The AND function basically enumerates the outcomes of an action, and the R function basically synthesizes a controller that's correct for every outcome. Okay. So again, in the deterministic setting, the reason we have this every outcome is because we are unsure what observations we will see. So for each of the observations we see, we have to consider a controller that extends for each of these outcomes, right? Which is a kind of standard in most cases when you have planning and sensing. This is at the first level. At the second level, what the R function does is that it enumerates, as I just made clear, extensions of the controller for every possible observation, and then it recurses with the AND function. Okay, so they alternate this way, where the R function is really trying to construct a controller that works for every possible observation that we might see. This is a deterministic case. The key idea really, which is the actual treatment is fairly involved. You can have a look at the journal paper. But the key idea really is to basically have upper and lower bounds for the likelihood of goal termination. Okay, so the way it works is that every time you encounter a failing run, so a run that doesn't go anywhere, the upper bound gets decreased. Similarly, or analogously, if a goal run, if a run or history reaches a goal, you increase the lower bound. Okay, so you keep track of the upper and lower bounds, and essentially, when the lower bound exceeds the desired correctness likelihood, you're happy. You return the controller and say that this is good enough and this is a success. On the other hand, if the upper bound is lower than the desired likelihood, what it means is that none of the extensions of the controller for these non-deterministic actions is good. So we have to revert to the program state where this entire trajectory was even chosen in the first place. So you avoid action extensions that could lead to upper bound being lower than the desired likelihood. That's a key idea, but the technically we have to very carefully keep track of looping histories, which is what makes the mathematical treatment fairly involved. Just to say that we have a prototype implementation. It certainly handles the kinds of bridge walk domain that I talked about. You can give any desired likelihood and it will synthesize a controller for the appropriate likelihood. There are other domains we have tried. For instance, this is a two-dimensional version of the Hall problem I talked about in the first few slides, where you have a square-like structure and you have to go from A and return back to A, but you have the chance that each of these moves can fail. There's a chance that the agent move can fail and the agent will end up staying in the same state. But of course, you can use observations in that case to figure out have you moved or not. If it is a case that you expect to have reached one of the intermediate states B, C, and D. And again, we can show that for the desired likelihood, we can synthesize the appropriate controller. So that kind of wraps up the key ideas here. We have new theoretical results on a very generic technique for synthesizing finite state controllers in stochastic environments, allowing for highly granular specifications of termination and goal satisfaction. As I mentioned, this builds on again, a very generic technique for deterministic domains, but we have shown how it can be carefully extended for stochastic environments. The more important point here is that we can prove soundness and completeness of this algorithm, and this provides a very strong guarantee in terms of the synthesis problem. That's it from me, and Laszlo, thank you very much, and happy to take any questions.